Hey guys, it's Darius. Welcome back to InventBox. Today we're going to be talking about perspective. You can see that I've got this cube rotating. Still, it's though just the X direction and not the Z direction, so that you can clearly see that there's no perspective whatsoever. In fact, you might call this an orthographic projection, because the vertices, even though they get farther away, they don't get smaller or closer together and really, giving it that 3D look. And so when you look at it spinning in this direction, I mean, because it's a box, it kind of looks 3D, but you could also look at it in a way that makes it look 2D. And certainly not true to the real world, not as realistic. So we can fix that with applying some more matrix transformations that will give it that perspective look. The other thing is this guy gets stretched quite a bit with the width of the screen, and we actually can fix that with a perspective matrix, because it will factor in the width of the width or the aspect ratio. Okay, so we've been doing matrices all along pretty much. Right now we have one matrix, and we can apply lots of transformations to that one matrix, and we could probably even use that same matrix to apply a perspective effect. But I want to create a second matrix so that I can kind of set it and forget it, if you know what I mean. Generally, unless your window is constantly resizing and your aspect ratio is changing, you can just create the perspective matrix once and use it for keep using it, and then your other matrix can be used you can keep updating your other matrix to rotate things and move them around. So that said, let's create a second matrix. I'm calling it projection matrix instead of perspective matrix, because perspective is actually a type of projection. And you could create an orthographic projection, which would be more similar to what you're seeing right now here. And also, it's just convention. So we'll create a new identity matrix, and then we'll head back to the docs for matrix 4. And we will call upon the perspective function. And it takes kind of a few parameters, so I'll walk you through it. Perspective. So if I recall, the first parameter is the field of view. But it's the vertical field of view. And it is an angle in radians. So, for example, humans have an 114-degree horizontal field of view. And that means that everything that you can see, starting from as far left, like peripheral, to right peripheral, well, maybe not including your peripheral, anything that you can see pretty well with both eyes, is about 114 degrees apart. And that's horizontal from left to right. Vertical, I'm not sure what the number is, and honestly it's not an exact science because it'll look pretty good no matter what number you put on there, and we can play with it. But I mean, choose something you think is reasonable. So 75 degrees is somewhere in between a 45-degree angle and 90, of course. And I feel like that seems pretty good. But it's in degrees, so we've got to multiply by pi and divide by 180. Next guy is the aspect ratio, which we can obtain just by dividing the canvas width by its height. This is why you'll have to recalculate the projection matrix if your window size changes. Or you could just reload the page, and that might be good enough for you. This is also what's going to fix our stretching effect. And now we can define boundaries on the sort of virtual camera. And the first one is the near cull distance, or the near cull plane. And that's a minimum. How close to the screen, how close to the camera can objects get before they kind of pass through and go behind the camera and go out of sight? So intuitively, you could set this something to really small. That's going to be a 1/10,000th of a unit. And so that means as soon as objects get super close to the camera, they will disappear because they'll go behind you. You might be tempted to set this to 0 so that they don't get clipped at all until they actually do pass behind you. But mathematically, that doesn't work. The near cull plane cannot be 0, and it also can't be negative. So you can't set it behind you, which that actually doesn't make any logical sense at all, because if it's behind you, you can't see it anyway. So anyway, just set it to something pretty small. For a really weird effect, you could set it to a larger number, and then you'll see it in your screen, it'll be getting closer to you, and then it'll suddenly disappear. And that may not be what you want, but you're allowed to play with these numbers. Hey, the worst thing that can happen is you throw an error and everything disappears, right? And now we have the far cull plane, which I usually set to a pretty high value. That is, as things get farther and farther away, they'll suddenly disappear. A far cull plane could be used to improve performance, just so that you're not always drawing everything. And if you have a really big map, you might not want to draw 5 million trees, only the closest 2,000 of them, you know? So you could pretty much set a maximum distance, and everything outside of that doesn't get rendered. But you still want it to be fairly large. You could set it to null, and I'm pretty sure that is treated as infinity. Or 10,000 will be good enough for me. We haven't used our projection matrix yet. The cool thing about matrices is that just like how you can store multiple transformations in a matrix, you can multiply two matrices together and sort of combine them. And then if you had two transformations on one and one transformation on the other, all three will be applied when you multiply them together. So they're like a cumulative. But the order that you multiply them really matters. So let's be careful about this. We actually will need to create one more placeholder matrix, which I will call final matrix, and it will be the result of the multiplication between both of them. And it will be what we upload to the shader program. Alright, so with this multiplication, using the multiply method, and of course the output is the final matrix. And now we'll pass in two operands, the one we just called matrix and the one we called projection matrix. And like I said, the order matters. And it turns out that the second operand, those transformations stored in there, in our case the translate, scale, and rotate, will be applied first onto your vertices, and then the projection matrix, the first operand, those transformations get applied. Okay, so I know this is very verbose for a multiplication. From more of a mathematical standpoint, if you had P for projection matrix and M for our, well, you would call this a model matrix because it's transforming your 3D model. So P times M would first apply the transformations in M and then do all the perspective stuff in P. And that's important because if you accidentally did the projection first, then all of your translations would be goofed up because the perspective, I think it would mess with the coordinate system. And you know, maybe it'd be a fun thing to try, just see how weird it looks. My file is saved, so that can't be the issue. Oh. What's probably happening is now that we've got a projection going on, see how our object isn't being translated in the Z at all? So it's right there on top of the camera, and it's probably being clipped off. That's my assumption. So let's translate that in the negative Z, which is out away from the camera. And there you can see it doesn't matter about the size of the window anymore as long as we reload the page. I'm going to get rid of the scale. It's just making everything tiny. There we go. Let's get rid of that guy. Whoop, and we can put our other rotation back. Whoop. Oh. Let's see, what else can we do? Get rid of our colors from the last video. I think JavaScript likes green because these are supposed to be random colors. Okay, well, it's not my place in life to criticize the JavaScript random engine, but that is pretty cool. And you can clearly see at this point the perspective that's going on here. And I know I had it like this before, but yeah, the perspective is obvious, and it looks pretty good. So now let's do some playing. Let's play around with this stuff a little. Number one, what happens if you go with a wider viewing angle, like 120? Well, it pretty much just looks like everything got smaller, which intuitively makes sense, because if you have a really wide viewing angle, you can see everything at once, and you can see a lot of stuff at once, and so you have to fit all of that onto the screen. And if you have a narrow viewing angle, you don't have to focus very much at all on anything. You know, you only have a tiny bit of data, I guess. So it's sort of like telescoping in on one point. So you can find something, you know, 90 degrees works pretty well. 75's pretty good. And how about this clipping distance? Let's change our near call and try to clip off the front of the box. Looks like we haven't got there yet. Where is this thing? -2 units. So in theory, I should get half the box here. Oh, that's pretty neat, isn't it? So the half the box that is closer to me is actually getting intersected by the near plane, and it's being chopped off. And we can set this back to close. What happens if I set the far clipping plane? You'd never know, because it is clipping it, but it looks normal, because from our perspective, we can't see the back of the box at all. How about infinity? I'm not sure that's I wish I could tell you, but I'm pretty sure that null and infinity are, the documentation said that they are, that null and infinity are valid, but I'm telling you that is not seeming very useful to me right now. Let's see, what if we set it to oh, that's kind of cool. So now only the corner that's closest to us is not being clipped. These are just, you know, demonstrations and examples, because obviously it's not very likely that you're going to be wanting to clip off that close to your camera. But it makes a really great visual to kind of help understand it. Well, I'd say this has been a pretty fun video. You know, just getting to mess around with the WebGL engine a little bit. So I'll see you in the next one. If you got any questions, leave them in the comments below. Thank you for watching.